Let's get started then with Chapter 3, Lesson 7. Give you something to think about here, a little word puzzle. H-I-J-K-L-M-N-O. A little tricky, see if you can come up with that one. So, right off the bat, we find out that Lesson 7 is about perpendicular lines and parallel lines, both of which you're probably pretty familiar. We've got a couple theorems about them that we're going to have to take. One a little tricky. First of all, have you ever been to that spot? Maybe some of you have. A little closer, it's known, as you see the label on the map there, as Four Corners. And if you go to Four Corners, you can actually stand in all four different states at the same time. Here's a little close-up of that circle in the middle. And maybe you can guess why the author has chosen that. Yes, that's an example of perpendicular lines. Once you give a shot at coming up with a good geometry definition of perpendicular lines, maybe you've got one. Pause it and give it a try. And if you're back, here is our definition that we're working with. Two lines are perpendicular if and only if they form a right angle. Some emphasis on that idea there. If they form a right angle, makes lines perpendicular. Now we're going to have a theorem that pretty obviously there will be four right angles there when lines are perpendicular. But if we were to just take this and this, it wouldn't form four right angles, it would form one right angle. So our definition is two lines are perpendicular if and only if they form a right angle. Keep that in mind when you're memorizing this definition. You might be saying, yeah, but it's two lines. Don't they go on forever? They do. But we're just going to keep this as our definition of right angles. And just some symbolism. So there we have line AB. And then we talk about this perpendicular, that little symbol. You can draw that on in your pictures. That means perpendicular. And there's line CD. Two lines are perpendicular if and only if they form a right angle. So with the proof today, I'm going to introduce something new. So far we've been doing two-column proofs, formal two-column proofs, where we make a statement on the left and then we give a reason on the right. Usually we start with a given and then build off of that. We're going to start today with a different approach, paragraph proofs. Each year, quite a number of students prefer to do paragraph proofs, and many times that's an option for you. The idea is you simply use sentences or phrases to make statements and then defend what you do in that sentence or in those statements. We're going to try it on our new theorem today, Theorem 7. Perpendicular lines form four right angles, which seems pretty obvious, but we do have to prove it. So there you see our theorem. All we're given is perpendicular lines. There they are, M and N. And we try to prove that M and M form four right angles. So you might kind of try to think backwards. How could we get all four of these angles over here to be right angles? Backwards is really a good way to go many times. In order to say angles are right angles, you would have to say what about their angle measure? Right, they'd have to be 90 degrees. How can we get them all to be 90 degrees? Well, we know this is perpendicular, and we know the definition of perpendicular. We just had it. Form a right angle. So if this is a right angle, by definition, we know it's 90 degrees. So we've got one of them here 90 degrees. Ooh, and what are 1 and 3? Yes, vertical angles. And what are 1 and 2? What relation do they have? Well, they're a linear pair. And the angles of a linear pair, by a theorem, we know are supplementary. So their sum would have to be what? Right, 180. And if this one's 90, this one's 90. Angle 2 would have to be 90. And then look at angles 2 and 4. They're vertical angles, aren't they? So they would also have to be equal. So 4 would be 90, making them all right angles. So let's see how we do that in a paragraph proof. Because M and N are perpendicular in the given, they form a right angle by definition, and we call it angle 1. Angle 1 is 90 degrees by definition because it's a right angle. 1 and 2 are a linear pair, so by theorem they are supplementary. Angles of a linear pair are supplementary. Because they are supplementary, 1 plus 2 equals 180 degrees. That's the definition of supplementary angles. So angle 2 equals 90 by subtraction. We had angle 1 was equal 90, and if we have 1 and 2 are 180, we can subtract angle 1 90 degrees from both sides. So 2 is 90 by subtraction, making 2 a right angle. So we're halfway there. We were given that 1 is a right angle. Now we know that 2 is a right angle. Now we're ready to use those vertical angles. So we just said 2 is 90 degrees and 2 is a right angle. 1 and 3 are vertical angles. 2 and 4 are vertical angles. That means 1 and 3 have to be equal by substitution. You know what, a better reason there would be vertical angles are equal. I should fix that here. Vertical angles are equal. And so we can also say 2 and 4 are 90 degrees because vertical angles are equal. That means 3 and 4 are also right angles. By definition of a right angle, it equals 90 degrees. So now we had given that 1 was a right angle, 2 is a right angle, we proved, and now we've got 3 and 4. So we've proven our theorem that says perpendicular lines, M and N, form 4 right angles. So a formal 2-column proof, how would that look? So there's a spot for you. Maybe you should want to pause that and give that a try. In class we may take time to do this, but in the slideshow we're not. We are going to move on to this, however, the corollary to the definition of a right angle. Again, a corollary, it's a theorem, but it's so closely provable from something else, we don't call it a theorem. I think you're going to understand why on this one. So we've got 2 perpendicular lines, and we just proved by theorem that it forms 4 right angles. Well, our corollary is simply this, and we use this 119 times yet this year. All right angles are equal. Well, yeah, right angle's 90, so sure, that makes sense. This is a handy one. We use it a lot. All right angles are equal. Here's the theorem I said was going to be a little tricky. If the angles in a linear pair are equal, how do you think that's going to go on? Several things you could say, couldn't you? If they're equal, well, it's a linear pair, so they're supplementary. Well, then if they're supplementary and they're equal, they must both be, supplementary is 180, they're equal, right? They're both 90 degrees, which means they're both what kind of angles if they're 90 degrees? Got that? Right angles. Well, and if these 2 lines meet to form right angles, what can you say about those 2 lines? They must be perpendicular. So here's how that theorem goes. If the angles in a linear pair are equal, then their sides are perpendicular. So here's the proof of that in a paragraph proof. So we're given 1 and 2 are a linear pair right here. And we're given that they're equal. All we need to do is try to prove that OB is perpendicular to AC. Here's another good example of working backwards. How could you say that OB and AC are perpendicular? Well, if you could get them to form a right angle, that's the definition of perpendicular. It forms a right angle. Somehow we have to get one of these to be a right angle. Well, it's a linear pair. We know that the angles of a linear pair are supplementary, so we know that their sum has to be 180 by definition of supplementary. And if they're equal, it would be 180 divided by 2 is 90. If they're 90, they're right angles. So we've got OB and AC perpendicular. Here's the proof in a paragraph form. Because 1 and 2 are a linear pair, which was given, they are supplementary by theorem. So angle 1 plus angle 2 is 180. That is the definition of supplementary angles. Their sum is 180. We're going to go back up to the given. Since 1 and 2 are equal, we can say 1 plus 1 is 180. Got the reason there? That would be by substitution. And then we simplify and get 2 angle 1s are 180. So now if 2 angle 1s are 180, we're trying to get to perpendicular, which means we need a right angle. Well, sure, let's divide both sides by 2. Gets us 1 equals 90 degrees. Are we there? Can we say they're perpendicular? No. The converse of definition of perpendicular is that if it forms a right angle, they're perpendicular. This is not a right angle yet. This is a 90 degree. Yes, that is so close. But we do have to take the step and say angle 1 is a right angle by definition. Then by definition, two lines that form a right angle are perpendicular. If they form a right angle, so OB is perpendicular to AC. So we've proven up here that if the angles in a linear pair are equal, then their sides are perpendicular. One more real quick slide on these two lines. We call these two lines parallel lines, and you see the symbol down there. Two things that have to be true about parallel lines. Pause it and think about it a little. What makes two lines parallel? If you're back, what would make them parallel? Well, they obviously can't intersect. If they intersect, they're not parallel. The other thing we have to throw in there is that they have to be in the same plane. Picture a line starting right here and coming straight out at you, right out of the screen, coming right up at you. Those two wouldn't intersect, but they would not be parallel because they're not in the same plane. So there's our definition to memorize. Two lines are parallel if and only if they lie in the same plane and do not intersect. Memorize that one for this chapter. Let's then get into the problem sets here. Obviously you don't have to watch this part, but it may help. Maybe you've seen this fact when you used to put a pencil in a glass of water, how the light seems to be refracted and the pencil is bent. Well, in this figure we're given that AB intersects CE at point W, right there. That's all we're given. And now we need some reasons. So ask yourself some of these questions. If 5 plus 6 is 90, then 5 and 6 are complementary. Why can you say that? Again, notice this is our hypothesis. This is our given, basically. And here's our conclusion, and you have to give a reason for that. Same idea here. Just read through the given, the if, and why can we say the then part. Keep working your way through it, assuming you're pausing when you have to. Now we've got SWR and AWE are both right angles. Then we're going to say that they're equal. Why can you say that? Look back through this lesson in your book. They're both right angles. We have a corollary. If 2 and 3 are supplements of RWB, we're saying that 2 and 3 are equal. This is almost stating the theorem right here. So find that reason. If 2 equals 3, if 2 equals 3, then WA bisects angle SWR. Well, sure. What does a bisector do? So we'll give a reason for that. And then if AWC equals AWE, then we're saying that AB is perpendicular to CE. Remember that difficult theorem that we had. Right now we just said that the angles of a linear pair were equal here. Check out the theorem. This one just checks your understanding of parallel lines, so check the definition out there and give an answer to number 8. We've got a dartboard, and I've put in the metal lines. I've put them in different colors. It's to help you with the last question there. So you work through what relations the lines have to one another, like all of them together. What relation do they have? Why do angles of opposite sectors? So a sector would be like between this yellow line and the red line, and then the yellow line and the red line here. Those would be sectors. Why must those angles be equal? Why must some of the pairs be supplementary? For instance, if I went this yellow one to the green one, and then the green one to the yellow one, why would those be supplementary? And then here's where I gave you a little help. How many pairs of perpendicular lines do there appear to be? A Necker cube, named after a Swiss guy, shows a cube there drawn in like 3D. And I've given a little help here. Which edges are parallel to AB? There's AB. Edges means more than one. Get as many as you can that are parallel to that. Picturing that as a cube. And perpendicular to that one. Perpendicular has to form right angles. Neither parallel nor perpendicular to the line I've got there, CG. Neither parallel nor perpendicular. You should be able to get at least, you should be able to get 2. Maybe more, maybe 4 even. See if you can find them all. And finally, which edge is in back the cube? CB or HE? Which is in back? This one really depends on how you look at it. Did you see it this way? Or did you see it this way? We're even going to take geometry out into the desert. We've got some sand that was wet at one time. It's dried up, and as it does, it cracks. And they're suggesting that a lot of the cracks seem to meet in right angles. Maybe that one there, kind of. There's a right angle there, it looks like. So you could look around and find several right angles. There's one down there, maybe another one there. The line segments in the figure below represent 2 cracks, A, B, and CD, meeting at point B. So here's one crack, there's another crack, and they meet here at B. And now some questions. 1 and 2. How are they related with respect to their sides? So there's the side of 1 and 2. There's a side of 1, and there's a side of 2. There's actually 2 parts to that answer, aren't there? How about their measures? If you had the measure of those, how would they be related to each other? It says when the mud cracks, these 2 angles, 1 and 2, tend to be equal. If they are, question 19, what's their measure if they're equal? What kind of angle would that make angle 1 here? And if that's the case, what does it prove about the cracks A, B, and CD, if what you said in number 20 about 1 is true? And then he wants you to revisit that theorem. That's that trickier one that we worked on near the end of the lesson. This one's a good challenge to make sure you understand what you're doing here. Let's look at the given here. Angle 1 is a right angle, but angles 2, 3, and 4 are not. So think about that a little bit first. If this is a right angle and this one is not, that means that's 90, but this is not. Well, that seems to mess up an idea that we had earlier, certain angle pair. If this is a right angle, but this one is not, this one's 90, but that one's not, it says something about this proposed line here. Same with 1 and 2. There's a few things going on, and then he's going to ask you some questions here and have you think about and explain why. Is it correct to conclude that any lines in the figure are perpendicular? Keep going back up to the given here and look at that carefully, and then explain. These last three are contradictions then that we get from the drawing. Keep the givens in mind. This is a good one to think about. And finally, is it possible that 2 and 4 could be vertical angles? These two, could they be vertical angles? Good question. Going to get a little practice with bisecting here. We've got a linear pair. We've got one of the angles, AOB. If that's 50, you know for sure what BOC has to be, and they ask you that right away. And here's the practice with construction. So make a good enlargement. It's a lot easier. And then do exactly what they say here in label. So I've kind of given you a reminder in case you forget. Look something like that. Name that one X. And that one Y. Doesn't matter where you put that little spot. Once you've done that now, there are some questions here. Think about it. Remember, this one started at 50. And this one you figured out had to be 130 to equal the 180. So now some questions. How large should BOX and BOY be? And measure them, see how close you got. How large is XOY? So this new angle that was created by the two bisectors, how large is that? You've got a similar drawing here in general terms, though. Notice they've bisected AOB and they've bisected BOC because these two M's have to be the same. That's what a bisector does. Same thing with the ends. So that's our given. And then some questions. So think about that. Why AOB and BOC supplementary? So you're basically forgetting about this line X and line Y on this first question. Now they want you 2M plus 2N. What would that have to equal? They're looking for a number. And then not 2M and 2N, but now just M plus N. Once you get that, you should be able to name the type of angle and give the reason why it is that type of angle. Once you've got that answer, I think it'll be a little bit easier to see this number 37, how OX and OY are related, and give a reason for that. All right, heading off, we've got a new given here. A is perpendicular to B. What's the definition of perpendicular lines? They form a right angle, just one right angle. So we've got that marked as a right angle. They've given the other measures of angles 2, 3, and 4 as n, 2n, and 3n. So first of all, write an equation for the sum of the four numbered angles and solve it for n. Going all the way around in a circle here, right? And that's a 90-degree angle, so get a good equation there and solve for n. And then find the measures of the four angles. Well, you're just using substitution, aren't you, once you have n? Once you have those numbers, they want to start to look at relations between 1 and 3, for instance, 2 and 4. All right, moving on to a three-dimensional drawing here of a waterfall. Gravity pulls water in a waterfall vertically downward to the horizontal surface. So think of this in 3D. These are actually right angles right here at WAB and WAC because it's perpendicular to the flat water. Here's that same drawing over here. And it's a short proof, 3 steps. I'm not going to say much about this. Give this a try. They start off with WA perpendicular to AB, WA perpendicular to AC, and they're looking for a reason. Then, based on this step, they want to know why WAB and WAC are right angles. A reason there. Then they want to know why WAB is equal to WAC, and that reason. Next, copy and complete the following proof. We know that 1 and 2 are complementary. So I'm thinking, hey, if they're complementary, I know something about their sum. And if that sum is 90, then I know that these two lines would have to be what? Because they're creating a right angle. PC is between PB and PD. Keep that in mind. It's between. That's a big hint to what's coming up here. If it's between, what can we say about the sum of those two angles? So here we go. We've got statements, and they're looking for reasons here. And then every once in a while you have to fill in a question mark. Okay, working that through. Keep looking back up at the given. And answer the reasons for each one of these. Here's a little hint. PC is between those two. Looking for reasons right down to the bottom here. And number 7, they don't give you the step. But since it's the last one in the proof, you can guess what has to go in there. We conclude this lesson then with a fun set 3. Give this one a try. There's some sticky credit here for this one. You need a file card, stiff sheet of paper. You can get it from me. Cut them out. Try to form the letter F. I think that's all it says, huh? Try to get those shapes to form the letter F. That's it, huh? There are the shapes. You'll have to trace them in your book and go find them. So that's it then for this lesson.